Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to be going over writing electron configurations. In particular, we're going to go over orbitals and how the electrons are put into the atoms. Okay, so let's get into this. So what you see here are some examples of what orbitals are. So we have an s orbital, a p orbital, a d orbital, and an f orbital. We're going to learn about what those are as we go through this presentation. Okay, so first, you don't need to do anything with this. We start with the Bohr model. This was created by Niels Bohr, and the Bohr model is what is known as the solar system model. So he thought that electrons were orbiting the nucleus, much like planets orbiting the sun. So the nucleus is in the center, and the electrons are uh, going around the nucleus in different orbits, just like our solar system. So that's called the Bohr model. So he was wrong, though. The atom as we know it today, the model is more like bees around a hive. So the closer you get to hive, the more dense the bees are, right? So the farther away you get from the hive, the less dense the bees are, the less likely you're going to run into bees. But if you get closer and closer to the hive, the more likely you are to get bumped by a bee or be in the presence of bees. And the model of the atom, as far as electrons are concerned, is very much like that. So when we're talking about atomic orbitals, we're really talking about where electrons are most likely to be found, just like, where are bees most likely to be found. So if you're closer to the hive, you're very likely to find some bees near the hive. But if you move away from the hive, the likelihood or the probability of running into a bee it goes down. So when we're thinking about orbital diagrams, you're thinking about a space around the nucleus in which you have a high probability of finding the electron. And that's all we know. So in the Bohr model, we thought we knew exactly where the electron is. It's on these distinct orbits that we can point to. But in reality, the electron exists in some space. We don't know exactly where it is, but we know we have a high probability. We know with a high probability where it is within a certain space, and that probability is like 90%. So that's what we mean by an orbital. It's basically it's the space around the nucleus in which we have a 90% probability of finding the electron. And so here's an example of what we might think of as a orbital. So here we have a kind of a probability map, and we have this spherical shape here. The nucleus is in the center, right? And we have this electron cloud. So again, it's like bees around a hive. So close to the center, you have a lot of bees. That's you can see you have a dense. You have the density of the dots is very thick, but as you get farther from the nucleus, the density goes down. So it's not as dense here. So that means you have a high probability of finding the electron closer to the nucleus and a lower probability of finding it away from the nucleus. And this is what we call the electron cloud. And this, ladies and gentlemen, is what we mean by an orbital. It's this space within the cloud that we have a 90% probability of finding electrons. So that is what we mean by an orbital. So how do we describe orbitals? There's 4 different ways we describe orbitals. So one is by the energy level. So when we talk about an orbital, we're going to mention a number, 1, 2, 3, 4, 5, 6, 7. And that number represents the energy level of the orbital. What energy level is that orbital at? So that's 1. 2 is shape. We're going to identify the orbital by the shape and what level it's at, or sublevel it's at. So there's a sublevel that the orbital belongs to that is represented by a letter, S, P, D, or F. And that indicates shape of the orbital. What kind of shape does it have? 3, we're going to have orientation. So we're going to be able to describe the orientation, like how is it oriented in space. We have the 3 axes of the Cartesian coordinates. You have your x, z, y axis. And so we can describe the orbital according to its orientation. And finally, we can tell how many electrons are in each of the orbitals. And we're going to find that the maximum number is 2. All right, so let's talk about energy levels. So energy levels, there are different energy levels. So the orbitals can be either in energy levels 1, 2, 3, 4, 5, 6, or 7. We only go up to 7. We could go higher, but for the purposes of our class and the fact that the periodic table only goes up to 7, we're only going to go up to 7. So n, this n number, that's the number of the energy. So we use this small letter n. Number 1 is the lowest energy and it's closest to the nucleus. So this is important to remember. The closer you are to the nucleus, the less energy you have. The less energy you have, the closer you are to the nucleus. So here we kind of have a Bohr model picture here, which is makes it easier for us to understand. So here we have one circle around, or one sphere. It could be around the nucleus. That would be energy number 1. That's the lowest energy. It's the closest to the nucleus being in the center. And next we have n equals 2. That would be the next higher energy level. N equals 3 and n equals 4 and so on. So the bigger the number, the higher the energy. The higher the energy, the farther away you are from the nucleus. So this is like rungs on a ladder. So if you climb a ladder, the farther you get up the ladder, the farther you are from the earth. And so you can think of this as potential energy. So the higher energy, the higher you go, the more energy you have, the farther away from the ground you get. So think of the energy levels as the rungs on a ladder. All right, let's talk about energy shape. So when we're talking about energy shape, or I'm sorry, we're talking about orbital shape, they go into 4 different categories. There could be more, but the ones that we know of is 4. So we have S, P, D, and F, and each of these represents a sublevel, right? And in this sublevel, there are orbitals that have a particular kind of shape. So you have S sublevel, P, D, and F, and we're going to talk about those in a moment. And here you can kind of see the different shaped orbitals. Here you have an orbital that's spherical. Here you have an orbital that is more like, dumbbell shaped, or it's got like two balloons connected at the center or something like that. So this is what we mean by the shape of the orbitals. So this spherical shape is the s orbital. So all s orbitals are going to have a spherical shaped space here. So again, the orbital is defined as the region or space in which you're going to have a high probability of finding the electron. So for an s orbital, we have a high probability of finding an electron within this spherical shape. Okay, we don't know exactly where, but we have a high probability of it somewhere in here. And the next orbital is the p orbital. So here, if the electron is in the p orbital, then it's going to have a high probability of being found in this shape. And it's kind of a weird looking shape. So it's not going to be really found outside here. So it has a low probability of being found outside this shape. But within this space here, it has a high probability of 90%. So this has a weird looking shape. And it's along the z-axis here. So p orbitals will tend to have this sort of shape. And here are the orbitals that we know of so far. So there's only one type of s orbital, right? So the s orbital looks like this. All s orbitals look like this. And then for the p orbitals, you have 3 of them. And they all have the similar shape of two balloons being connected at the center, or two like a dumbbell shape or something like that. So here you have three p orbitals. You have one along the x-axis, and you can one along the z-axis and one along the y. So you could see here the three different orbitals. They have the same shape, but look, they're oriented in space. So remember, that was one of the ways we could describe an orbital, is that it's oriented in space differently. So here's one orbital, and here's another orbital, and here's a third orbital, and they're all oriented in space differently. Now, we got some weird looking orbitals here. So you can see that these orbitals here, these are the d orbitals. And the d orbitals, we have 5 of them. If you count 5, 1, 2, 3, 4, 5. You can see that instead of having 2 lobes, you have 4. And each of the 4 lobes here is oriented in space differently. Now here you have a weird shape. You have a dumbbell shape, 2 lobes with a donut, right? So that's strange. But this is, again, these are the 5 different d orbitals that you could find, and they have different regions of space to find the electron. And then finally you have the f orbitals. And again, the f orbitals, you can see that they have 6 lobes, right? Or is it 8? I can't remember. So it looks like it's 6 for some of them, 8 for another one. So different orbitals, but they have a similar kind of shape, but the orientation is different. So you're not going to need to know how to draw the d or the f orbitals, but you will need to know how to draw the s and the p. So as I was saying, orbitals can have different orientation. They can be oriented along the axes differently, or the planes of the axes. So x, y, z axis. So if we're looking at, say, the p orbital, as I said, we have 3 different p orbitals. We have one called the px, which is aligned along the x-axis. We call that px. We have a second one along the y-axis, so we call that the py orbital. And we have a third one along the pz axis, so that's called the pz orbital. So each of these orbitals are different, and they can each have electrons in them. So it's not like the same orbital is aligned differently along different axes. These are 3 different orbitals in which you can find electrons. And finally, the fourth thing is we need to describe the electrons in an orbital. So we said each orbital is only allowed to hold 2 electrons. That's the maximum that any orbital can have, is 2 electrons. And the reason is because you can have only one of 2 spins. An electron can be spin up, or it can be spin down. And these are not literal spins. These are just what they call the electrons. It comes out of math, and you don't need to worry about that. But we just call them spin up, spin down. So how we describe the 2 ways that the electrons can be. So you can only be either spin up or spin down, and you can only have 2 electrons in an orbital. So now let's talk about how can we tell someone exactly where an electron is. So we have these electrons in an atom. Like, let's say we have 25 electrons. Where do these electrons go? How do we describe, or how do we tell someone where these electrons are at? And they're in the orbitals, and the orbitals have different energy levels. And so we're going to learn, like, how do we put the electrons into these orbitals in the atom. So I want you to picture some sort of house or an apartment building or a hotel that has floors in it, and each floor has a certain number of suites, and each suite has a certain number of rooms, right? So let's imagine that, and we'll talk about how we can understand where the electrons are at. So think about where you live, right? So you live in the state of California. Maybe you live in Pleasanton City. So we describe the city we're in. So state, city. And we also will mention the street, right? And then we'll give our house numbers. So each part of the address tells you something about where you live, and you get more and more specific, more and more uh, you know detailed, I should say, maybe, of where you live. So, I live in California. Where in California? I live in, say, Pleasanton. Where in Pleasanton? I live on uh, Ferdinand Avenue. That's the street. Well, where on the street, right? So then you give your house number so you can pinpoint exactly where I live. This isn't exactly where I live, but it's just an example. Okay. So you can write an address of where you live. And so, in the same way, you can kind of write an address of where a particular electron is in the atom. So, couldn't you write an address for where the electrons are in the atom? And yes, you can. So when we're talking about like the state, that would be like the energy level. So what energy level is the electron is at? So you can say the energy level, but then you can be more specific. Like, so the city might be the shape of the orbital. That would be like the sublevel. So we have an energy level, we have a sublevel, and then the street would be like the orientation. How is it oriented in space? Is it along the x, the y, the z axis? And then the house number, that would be like the spin of your electron. Is the electron spin up? Is it spin down? And we can combine all of these uh, to kind of write an address for each electron. So in electron configuration, this is our address. So the number, so in this is an example of an electron configuration for a particular electron. So you can say it's the number 2 is the energy level. So that's the first thing. P would be like the shape or the sublevel that the electron is in. So that kind of tells you something about the shape of or type of orbital. And it's the type of orbital it is because it's at a sublevel, right? The orientation kind of tells you what orientation that particular orbital is at, right? So in this case, it's in the x orientation along the x-axis. And then we usually will talk about spin up, spin down by plus or minus 1/2. So that's how they indicate spin up and spin down. Spin up is plus 1/2, spin down is negative 1/2. Remember, these numbers come out of high level math, so you don't need to worry about that. But the important thing is that each of these parts tells you something about where the electron is at or what electron is in this particular area or orbital. So you can put electrons in the various orbitals here. So you can put 2 electrons in the 1s orbital. So you have one orbital that's at the 1s. You have energy level number 1. So both electrons are at energy level number 1. Both of them are going to be at the sublevel s. So they're in an s orbital. So there's only one s orbital at this sublevel. And so each electron is going to have a different spin. So you could fit 2 electrons in this orbital. One is going to be spin up, the other is going to be spin down, and that's indicated by the plus and minus 1/2. And then that would be your first 2 electrons would go into that orbital. And then the next 2 electrons would go into another orbital, and that's at the second energy level. So these guys are at the second energy level, and they're in an s sublevel, which has one s orbital, so it's got a spherical shape, right? So we've got a spherical shape orbital, the 2s, and then each of these electrons are going to have opposite spin. So you have 2 electrons at this energy level in this sublevel s at s orbital, and we have another 2 electrons at this energy level. And then if we go to the second, or I should, the next sublevel, right? So now we're at a sublevel P, and we're still at energy level number 2, but now we've gone to another sublevel, which is the P. And P indicates that the electron or the orbital that the electrons are in are dumbbell shaped. They have, or petal shaped, if you want to remember P for petal. So S for spherical. And so here we know that we have three p orbitals. Each orbital is oriented differently. So here at the p sublevel, you have three p orbitals. You have the px, and two electrons can go into the 2px orbital. So you can have a spin up electron and a spin down. So that's two electrons in this orbital. And then you have the py orbital, so two electrons can go in there. You have spin up, spin down, so that's two electrons in the 2py orbital. And then you have the 2pz orbital, so two electrons can go into there, spin up plus 1/2, spin down minus 1/2. And so you have 6 electrons total can go into this sublevel. So you can think of this as an energy level with one sublevel. And then you have this second energy level, and it has two sublevels. So you have the S sublevel and you have the P sublevel. In the S sublevel, you have two electrons. You have one orbital, and that's the S orbital that can have two electrons. And in the second sublevel, in the P sublevel, you have three orbitals. Each orbital can hold two electrons. And so that means you have a total of 6 electrons in this sublevel. And so that we can write this electron configuration just like this. So we can write the energy level, the sublevel, and the number of electrons at that sublevel. So we have here, energy level number 1. We're at the S sublevel, and there are 2 electrons at that sublevel. So here we are here, 2 electrons in that sublevel. And then we go to the second sublevel, and we could write that. So energy level number 2, we're at the S sublevel because we have S here, and we have 2 electrons in that sublevel, spin up, spin down, plus 1/2, minus 1/2. And then at the second sublevel, at energy level number 2, this is the 2p sublevel. And here we have, again, 3 orbitals. Each orbital can hold 2 electrons. Each electron has a different spin in the orbital, and so that's a total of 6. So we just write 6 for that sublevel. So 1s2, 2s2, 2p6 is the electron configuration for this atom so far, for these electrons. So we can identify where the electrons are by writing them in this notation. So if we want to describe where all the electrons are in the atom, what do we do? So we're going to shrink it down and only list the basics here. So the way we describe this is we do the energy levels, we're going to do the shapes of orbitals, and we do just the number of electrons in each orbital. So when we write it down, we are just going to write the energy level, the sublevel, and the number of electrons at that sublevel. And that number of electrons at that sublevel is going to be determined by the number of orbitals we have at that sublevel. So we only have one s orbital at each sublevel, the s sublevel. So that means we're only going to have 2 electrons because each electron can only hold 2. At the p sublevel here, there are 3 of those p orbitals, the px, py, pz, and so each of those can hold 2 electrons, so the maximum is going to be 6, right? And we would indicate that at each level. So we start at level number 1 and we work our way up to the higher levels. And so you can figure out what atom this is by adding up the superscripts here, because the superscripts represent the number of electrons at each sublevel for each level. And then you add them up, and so the total number of electrons should be equal to the number of protons in your atom if we're assuming a neutral atom. And so in this case, we have 16 electrons, so therefore this should be atomic number 16 for the number of protons, and that means it's sulfur. So we look up the periodic table for number 16 and we find sulfur. And so this here is an orbital diagram, And this is the chart that we use to show what order the orbitals go in. So each orbital has an energy level. So here you can see the energy level here, energy level number 1, number 2, number 3, 4, 5. And so you can see the sublevels here. So this is the 1s sublevel, number S2s sublevel. This is the 2p, and you'll see there are three different orbitals here. So at the 2p sublevel, and then you have the 3s sublevel, which is higher in energy. And then you have the 3p sublevel with 3p orbitals, the px, py, pz. And then you have the 4s, followed by, you got the 3d here. So this sublevel has 5d orbitals, and so on. So you can see that the orbitals and the energy levels and the sublevels increase from low energy to high energy. So that's the way we go. So the first thing, when you're filling in your orbital diagram, you pick an atom, first of all. Second, you find the number of electrons it has. And if we're assuming neutral atoms, that means the electrons is equal to the number of protons, and the protons is determined by your atomic number that's on the periodic table. Then what you do is you start putting electrons into the orbitals, and you use the orbital chart diagram to help you do that. So you put the electrons into your orbital diagram. And then you list, after you've got all the electrons in your orbital diagram, then you list the orbitals you used and how many electrons in each, and you work your way from bottom to top. And we'll talk about the rules in just a moment. So what are these rules for putting electrons in your orbital diagram? The first one is the Aufbau principle. So the Aufbau principle is that an electron occupies the lowest energy possible. So you're going to put electrons into lower energies first. So the lowest energy possible, or the lowest energy that the orbital that it can. So what does this mean? It means that you're going to fill your orbital diagram from the bottom up. Electrons are lazy. So remember, this is kind of like a building. It's like a hotel or an apartment building. And let's assume that the apartment building has no elevator, or the elevator is broken, just like the apartment building in The Big Bang Theory. The elevator was always broken, and they had to go up the stairs. So if you don't want to go up the stairs, then you're going to want to stay on the lowest floors possible. If the lowest floor is filled up, then you're going to go to the next lowest floor, right? So you don't want to go up a whole bunch of stairs. You want to go up the least amount of stairs possible. So then there's the Pauli exclusion principle. The Pauli exclusion principle says that no two electrons in the same atom can have the same four quantum numbers. What does that mean in normal English? That means that if there are two electrons in one orbital, one has to be spin up, the other has to be spin down. They can't have the same spin. They can't both be spin up. They can't both be spin down. They have to be opposites of each other. And so you can only have two electrons in one orbital at the same time, and they have to have opposite spin. Okay, so they can't have exactly the same address if we're thinking in terms of address. And finally, we have Hund's rule. So Hund's rule tells us that if we have orbitals of equal energy, they are going to each occupied by one electron before any orbital is occupied by a second electron. So basically what that's saying is, if we have, let's say our 3p orbitals are equal energy, we're going to put one electron into each p orbital first, one at a time, before we pair them up together. Once each p orbital has an electron in it, then you start pairing them up with each other one at a time. So what does this mean? It means that if there are more than one orbital at the same energy level, like we have 3p orbitals and we have 5d orbitals, all of those are at the same energy level. So the 3p orbitals are all at the same energy level. We're going to put one electron in each orbital first before pairing them up with each other. So if we're thinking about sharing rooms, like, so if there's different rooms in your suite of the hotel, then everyone wants a room by themselves first before you start, having roommates. Okay, so that's it for this video. Thanks for joining me. I hope you enjoyed this video. I hope you learned a lot. Please share this video, like this video, uh, hit that like button, subscribe to my channel, hit that notification bell so you can be notified by other videos I put out. Comment in the comment section. Let me know what you think. And thanks for joining me. Have a great day.